Hello everyone. Today I'm going to tell you about Ramsey Theorems for trees and a general private learning implies online learning theorem. And this is joint work with Simone Fioravanti, Hanneke, Shay Moran, and Iska Tsubari. Okay, so I'll start with a quick motivation. A learning algorithm gets as input training data, works its magic, and at the end we have a trained model that can classify unseen data points. For example, imagine that we want to design an AI medical doctor that predicts whether or not an individual is in high risk of getting a heart attack based on his physiological indices. In order to train our doctor, we need to provide it real-world medical data of individuals. But of course, the problem is that this data is private and highly sensitive. And we want to make sure that our algorithm preserves privacy and the model does not leak any private information of individuals in the training set. This is where differential privacy comes into picture, and why learning under privacy guarantees is an important problem. So in high level, our goal is to understand the sample complexity of private learning. And when I say learning, I mean pack learning, and private learning meaning pack learning with respect to differential privacy, abbreviated DP. So here we can see a quick reminder for formal definition. I will go over it very quickly. So in pack learning, we have a domain X, and we have a label space Y, and we have an unknown distribution over the domain, and an unknown target concept, age. The input to the learning algorithm is a sample of labeled examples, where the examples are sampled from the distribution and labeled according to the concept age. And the goal of the algorithm is to learn age and generalize well with respect to the distribution. Differential privacy is a property of a learning algorithm. So an algorithm is differentially private if for every neighboring dataset, meaning datasets that differ at most one entry, the probability distributions induced by running A on S and on S prime are very close to each other. How much close? This epsilon delta notion of closeness. So in other words, the question is for which learning tasks there exist private pack learners, and what is the sample complexity of those learners? This question is a fundamental question, and extensive research has already been conducted in this area. I'll mention just a few key contributions. So in 2008, the study of private learnability is initiated, and it has been proved that finite classes are DP pack learnable. A few years after, it has been proved that thresholds over infinite domains are not properly pack learnable, and later on we will see another connection between thresholds and private learning. Then, a few years after, it has been proved that for binary concept classes, private learnability implies online learnability, and the year after, the opposite direction has also been proved for binary concept classes. And later on, this equivalence has been extended for the setting of multi-class, but only with bounded number of labels. In this work, we focus on the implication private learnability implies online learnability, which we already said that it's true for binary concept classes. And the question that we ask is, does this implication continues to hold in more general learning settings? And the answer is that it does. So, okay, this is a good point to state our main result, very informally. So for any classification task, DP pack learnability implies online learnability. So let's introduce two learning settings that go beyond binary classification, which we covered in the paper. The first and well-known setting is multi-class classification over an arbitrary domain. So we have a class of functions, and the label space can be infinite. The second setting is partial concept class learning. A partial concept class is a class of partial functions, and we model a partial function as a total function from the domain to our label space together with this special label star, where we interpret age x equal to star as age is not defined on x. This setting is particularly useful to model natural data-dependent assumptions. For example, imagine that the domain is a high-dimensional space, but actually all data points lie on a low-dimensional surface. The label of points outside of the surface can be treated as undefined. It is worth mentioning that in the 21 paper, Alon, Hanneke, Holtzman, and Moran posed the question whether private and online learnability are still equivalent in the partial concept settings. And as we will see more formally later on, we answer one direction of this question, while the opposite direction remains open. The naive approach to show that private learnability implies online learnability is trying to extend the known proof for the binary case. Unfortunately, this approach fails. The reason is that the proof is tailored specifically for binary total classes. So in their proof, the authors relied heavily on the connection between thresholds and online learning. So a binary total class is online learnable if and only if, roughly speaking, there are not too many thresholds embedded in age. To make this idea more formal, we define two combinatorial dimensions. In learning theory, it is common that there are strong connections between complexity of learning tasks and combinatorial dimensions. In the case of private learning, there are two relevant dimensions, the Leaderson dimension and the threshold dimension. And the threshold dimension is used in the proof of private implies online learnability, which is the direction we are interested in this work. And the Leaderson dimension is relevant for the opposite direction. We start with defining the Leaderson dimension, which is defined using shattered decision trees. A decision tree is a full binary tree such that the internal vertices are associated with instances from the domain, and every outgoing edge is labeled by a different label from the label space. A tree is shattered if every root to leaf path is realizable by age, meaning there is a concept in age that labels the vertices on the path according to the labels of the path. For example, say that this tree in the picture is shattered, then there must be a concept in age that labels x1 as 0, x2 as 1, and x5 as 0. The Leaderson dimension is the maximum depth of a shattered decision tree. And the class is online learnable if and only if it has finite Leaderson dimensions. So in a sense, the Leaderson dimension captures online learnability. And in fact, this continues to hold in more general learning settings. For example, in multi-class and partial concept classes, etc., etc. The next dimension we define is the threshold dimension. The set of all threshold functions over a linearly ordered domain X is basically all step functions that are 0 below some X in X and 1 above. The threshold dimension of a class is the maximal number D, such that we can find D points in the domain, and when restricting age to these D points, we get all of the thresholds over them. So, fact. For binary total concept classes, the threshold dimension and the Leaderson dimension are finite together. So in other words, for binary classification, the threshold dimension characterizes online learnability. And this fact is crucial for the proof of private implies online learnability for the binary case. So an obvious question would be, is this continue to hold for more general settings such as partial concept classes and multi-class? And the bad news is that it does not hold for more general classification tasks. So let's go back to the binary case proof. So the proof starts by taking a binary total class with letters on dimension at least d. And the first step is basically a reduction to one-dimensional thresholds. If the Littlestone is at least d, then there is a large number, as a function of d, of thresholds embedded in H. Then the second step is applying a Ramsey theory type attack on privacy and deducing a lower bound on the sample complexity of private learners for H. This lower bound tends to infinity as d tends to infinity, which completes the proof. But as we just mentioned, for general classification tasks, this very first step fails. And therefore, we understand that we need to reason directly about Littlestone trees without going through one-dimensional thresholds. For that reason, we developed several Ramsey theorems for trees, which we will discuss shortly. Okay, so this is a good place to state our main theorem more formally. Let H be a possibly partial multiclass problem with Littlestone dimension at least d. Then the sample complexity for privately learning H is omega of log star d. And an immediate corollary from this is that if the Littlestone dimension is infinite, then H is not privately learnable. And more generally, when online learning is characterized by the Littlestone trees, private learnability implies online learnability. And as I mentioned earlier, the opposite direction, whether online learnability implies private learnability in more general classification problem, is still an open problem and an interesting one, at least to my opinion. Okay, so this ends the part of the talk about private learning, and now we can move on to discuss Ramsey theory for trees. So the classical Ramsey theorem says the following: for every natural number d, there exists a large enough n such that for every edge coloring of the full graph over n vertices kn, there exists a monochromatic copy of kd. And the same results holds for m hypergraphs when we color hyperedges of size m instead of just regular edges. So now, instead of considering the full graph over n vertices, we consider the full binary tree of depth n, denoted Tn, and we color subsets of vertices of size n. The goal is to find a deep monochromatic subtree. But first, we need to understand what is a subtree. So there are several different ways to define a subtree. In this work, we define a subtree of depth d as a collection of 2 to the d plus 1 minus 1 vertices that are isomorphic to td. And when I say isomorphic, I mean that the relations of being left or right descendant are preserved. So as you can see in this picture, only the leftmost picture forms a subtree of depth 1. Those 3 vertices form a subtree of depth 1. Okay, as it turns out, our goal is just a bit too optimistic. We cannot find a deep monochromatic subtree always. And just for simplicity, we will focus on the case where we color pairs of vertices, i.e. m equal to 2. So let's see why there is no hope for a monochromatic subtree. Consider the following coloring of pairs, where we color pairs according to their type. We color left pairs with red, where a left pair is a pair of vertices such that one of the vertices is a left descendant of the other. Color right pairs with blue, and color incomparable pairs with green, where by incomparable I mean incomparable with respect to the natural partial order induced by the tree. It is clear that with this coloring, every subtree of Tn with depth at least 1 must see all of those 3 colors. Therefore, we cannot hope for a deep monochromatic subtree. But we can ask a different question. Is for any coloring of Tn, there exists a deep trichromatic subtree? And in general, maybe the right question to ask is what is the minimum number of colors tau such that for every coloring of M subsets there exists a deep tau chromatic subtree. For pairs, we saw that coloring pairs according to their type is a hard coloring. And as it turns out, 3 is actually the correct number. We proved that for every coloring of pairs of vertices in Tn, there exists a deep trichromatic subtree. And when we say deep, we mean that the depth of the subtree D tends to infinity, where the depth of the original tree N tends to infinity. Furthermore, we generalized the result for pairs, also for coloring general M subsets. We show that for every coloring of M subsets in Tn with K colors, there exists a deep tau M chromatic subtree. And the number of colors tau M is optimal, and actually it depends only on M, which is again the size of the subsets that we color. Also, we show that tau M is in fact equal to the generalized Catalan number, which is a known integer sequence. We also proved some upper bound on the corresponding Ramsey number. The Ramsey number of M, D, and K is the minimal integer such that for every M subset coloring using K colors, there exists a tau M chromatic subtree of depth D. We provided upper bound for the Ramsey number for pairs, meaning M equal to 2. And we also proved upper bound for the Ramsey number, assuming that we color only M chains, where M chains is basically a chain of size M of vertices with respect to the partial order induced by the tree. So this was all for today. Thank you for listening and see you at FOCS.